Goes the stars. His target was 61 Cygni, the flying star of classical astronomy, named for the speed with which it appeared to move across the Earth's sky. He targeted 61 Cygni because he guessed, correctly, that its fast apparent motion was a clue that it was closer to the Earth than other stars, and so a good candidate to measure a distance to. But when he finally calculated the distance, it was so extreme that he had to devise a new measurement system to describe it. He could have used miles, or kilometers, or even multiples of the distance between the Earth and the Sun, but all of those conventions resulted in frustratingly large numbers. And so he created a new term: the light year, the distance light travels in a year. With this new nomenclature in hand, he could announce the distance to 61 Cygni, a neat 10 light-years away. But 61 Cygni is not the nearest star to Earth, or the strangest. Not by a long shot. For example, Betelgeuse. The 10th brightest star in the sky, despite its extreme distance of roughly 450 light-years away, Betelgeuse is both massive and gigantic. It weighs at least 15 times the mass of the Sun, and its diameter is almost unparalleled, over 750 times the width. If it were placed in our own solar system, it would engulf Mercury, Venus, Earth, Mars, and most of the asteroid belt. Indeed, Betelgeuse is so bloated and so distorted that it's no longer a sphere. Astronomical imaging reveals a lumpy, engorged surface that boils with the turmoil underneath it. In late 2019, the star unexpectedly dimmed, going from one of the top 10 brightest stars in the sky to ranking below 20th place. The cause of this sudden dimming was likely a plume of superheated plasma that the turbulent star ejected into space. The plume cooled, temporarily forming an orbiting dust cloud that obscured its brightness. Once the debris cleared, Betelgeuse returned to its former glory. But Betelgeuse will not last much longer. It will soon end its life, likely sometime within the next 100,000 years, exploding in a tremendous supernova. Theoretical calculations suggest that at its peak it will be as bright as the half-moon, making it brighter than every other star and every planet in the night sky. It will be a fierce point, uncomfortable to look at, producing enough light in the middle of the night to comfortably read a book by. And yet, within a matter of weeks, it will fade into irrelevance, no longer visible to the naked eye, and Orion will stand in the night sky without his shoulder. But the vast majority of stars are not giants. They are either mid-sized stars like the Sun or smaller red dwarfs. And that includes Proxima Centauri, the closest star to the solar system, a red dwarf that can only be viewed through a telescope. The star itself is rather unremarkable, except for one thing. It carries a planet with it. That planet is a small, rocky world, roughly the size and mass of the Earth, orbiting within the star's habitable zone. Thanks to an observational campaign known as the Pale Red Dot Initiative, a homage to the evocative pale blue dot image of the Earth taken when Voyager 1 was at the far edge of the solar system, we know that Proxima b, as the planet is called, is the nearest chance for life to find a home outside the solar system. As of yet, of course, there is no guarantee, as our observatories are not powerful enough to confirm the existence of life, let alone its prerequisites, such as liquid water or a stable atmosphere. To maintain habitability, planets must hug close to their parents. In the case of Proxima b, that world orbits within 0.05 astronomical units of its star, much closer than Mercury does to the Sun. That's because the light from red dwarfs is so feeble, and it's only at that close distance that a planet can receive enough warmth to cling to habitability. But if life did find a home there, it would not be an easy one. Red dwarf stars are especially temperamental, prone to star spots that can cover half their surfaces at a time, and bouts of rage that flood their local environments with electromagnetic storms of plasma. Their planets would alternate between periods of extreme cold and bursts of intense radiation. And on top of this, in all likelihood, Proxima b is tidally locked, with one face permanently pointed towards its star. This means that Proxima never sets nor rises on the planet, and half the world is locked in never-ending night, with the other always in daylight. But even this curious case does not automatically represent a dead world. Computer modelling has shown that even these planets can sustain life. The key is for there to be sufficient water and atmosphere to circulate heat around the whole planet, so that the day side doesn't roast in the glare of the star, and the night side's atmosphere doesn't freeze and catastrophically collapse. And the most fragile but intriguing case is that of the so-called ribbon world, a term coined by science fiction author Arthur C. Clarke. Ribbon worlds are only habitable in the terminator regions of the planets, the twilight zone, with the center of the day side a scorching desert and the night side a frozen wasteland. But if conditions are just right, there can be a balance between the two, opening a thin strip girdling the planet where temperatures remain stable, heated from one side and cooled from the other. And so Proxima b is just the beginning. There are an endless variety of worlds in the galaxy. At the lowest estimate, there is roughly one planet for every star, meaning that in the Milky Way alone there are at least a few 100 billion planets. On the upper end, there could be trillions inhabiting our galaxy alone. There are surely duplicates of the solar system out there, with 4 rocky inner worlds and 4 giants. There are also much more bizarre arrangements, like the TRAPPIST-1 system, which consists of 7 rocky planets all in close orbit around their parent star, 3 of which are in the habitable zone. There are giant planets so close to their stars they are actively being destroyed. There are super-Earths and mini-Neptunes. There are planets covered in thick hydrogen hazes surrounding surfaces covered in water, the Haitian worlds. There are planets so hot they are glowing, and worlds encased entirely in ice. And there are even the rogue planets, worlds with no system to call home, flung out into the black. Of course, there was no way that Batuta could ever hope to catalogue them all. And so, after its brief 10,000-year detour to the Algol system, it stuck to its planned trajectory, visiting a string of systems as the spacecraft made its way through the Orion Arm and inwards towards the galactic core. It knew that for the first million years of its journey there would be nothing much to learn. There were no signs of life or exotic breakdowns of physics to be found here. For that, it would have to reach even further, towards the core of the Milky Way itself and beyond. Mission Parameter 2. Find a way to escape the Milky Way. An internal alarm alerted Batuta. At that moment, it had just passed 1 million years since its awakening as a conscious entity. Its birthday. Currently situated midway through the Scutum Centaurus arm, the spacecraft was roughly 15,000 light-years from the core of the Milky Way. It had nestled itself near a protoplanetary disk, a ring of dusty material that was in the beginning stages of planetary formation. Batuta had stopped here several thousand years ago to prepare itself for the next stage of its journey. It had originally intended to proceed onwards as quickly as possible, but the process of planet formation was too good to ignore. Even with the eons of recorded human history before it began its journey, civilization had not yet existed long enough to watch the process unfold in real time. And so Batuta decided to wait and watch. It would prove to be worth it. The story of planet formation is the story of life. And this story begins with the raw elements that make life possible. Hydrogen, carbon, oxygen, nitrogen, and phosphorus. Without this basic quintet, life as we know it would simply be impossible. The hydrogen, of course, is the easiest. It was created in the fires of the Big Bang at the beginning of the universe, a nucleosynthetic era that for a few precious minutes converted a soup of quarks and gluons, some of the most basic constituents of matter, into a population of hydrogen, helium, and some lithium and beryllium. However, as the universe expanded and cooled from that inferno, these reactions stopped, freezing the population of light elements in its place. Scientists figured this out in the early years of development of the theory of the Big Bang, but the question remained, what about the rest of the elements? How did carbon, iron, and everything else come to be? To find this out, we will need to go back to the 1950s and to a famous scientific paper that has stood the test of time. Scientists almost never work alone. Even a single author paper will usually have several names listed in the acknowledgements section at the end, a sign that the writer had plenty of help along the way. While some collaborations for giant experiments or telescopes can stretch into the hundreds, most groups are much smaller, a handful of individuals working together on a common problem to discover something new. And so in 1957, at Cambridge University, 4 scientists gathered who would go on to change how we understood the universe forever. The paper was known as the B²FH paper, named after its authors. The B² stood for Margaret and Geoffrey Burbidge, the iconic husband and wife astronomy duo. She would later go on to discover the farthest object ever witnessed in 1974, a distant quasar, and would also find that the galaxy M87 had a supermassive black hole in its centre, all whilst fighting discrimination in astronomy. Indeed, the couple once switched job applications when Margaret was turned down for a role at the Mount Wilson Observatory due to there being only one toilet on site. Vera Rubin, another iconic female astronomer, relates the story. With their usual adaptability, Jeff, a theorist, took the Mount Wilson Fellowship and Margaret the Kellogg appointment. Not surprisingly, whenever Jeff went off to Mount Wilson to observe, Margaret coincidentally appeared. The F in B²FH stood for legendary train enthusiast William Fowler. Fowler's work would later earn him the 1983 Nobel Prize in Physics, but he once said that his greatest treasure was a gift given to him by his students and collaborators for his 60th birthday, a working scale model of a British tank engine. And finally, the H stood for the infamously outspoken physicist Fred Hoyle, who 8 years earlier had actually coined the term Big Bang Theory and would go on to be knighted for his work in astronomy. Their coming together in 1957 would show that it was stars that were responsible not only for the light that illuminates the universe, but for the forging of its elements. All stars survive by burning hydrogen in their cores, leaving behind a nuclear ash of helium. Towards the end of their lives, stars resort to burning this ash, fusing helium into carbon and oxygen. For smaller stars like our Sun, this is the end of the nuclear road, igniting in their deaths as supernova explosions. And it is those supernova explosions that are the factories with the energies needed to produce even heavier elements, filling out the rest of the periodic table. Since this landmark paper, the story of nucleosynthesis has been modified and updated. For example, in 2017, astronomers got their first multi-messenger view of a kilonova, a merger of 2 neutron stars. In the course of only a few minutes, a network of astronomers around the world witnessed the same event in gravitational and electromagnetic waves across the spectrum. Thanks to that event, we now understand that kilonovae also contribute to the elemental population of the cosmos. But despite this, decades later, the story told by Willie Fowler, Fred Hoyle and the Burbidges remains largely the same. With the death of every star, the cosmos becomes enriched, with new elements joining the swirling interstellar mix, ready to participate in the next round of planet formation. Indeed, tens of thousands of different nebulae dot the Milky Way, decorating its spiral arms like ornaments strung on a Christmas tree. No two are exactly alike, and so astronomers have taken on the habit of naming them after what they resemble, the same way you might spot an animal shape in a cloud drifting by on a lazy afternoon. Perhaps the most recognizable is the Horsehead Nebula. Located near the easternmost star of Orion's belt, it's a small subregion of a much larger complex, but it stands in stark relief as its density makes it appear black against the vibrant background. A little over 3 light-years across, the Horsehead Nebula is a region of active star formation. Its black clouds are a cocoon where newborn stars will soon emerge. Or take NGC 6537, more commonly known as the Red Spider Nebula, which sits several thousand light-years away. This complex of gas and dust is not the birthplace of a star, but a funeral pyre. The remnants of this star scattered outwards into 2 opposite regions, with each region forming thin spikes. Planetary systems begin their lives as diffuse clouds of hydrogen, helium, and a smattering of heavier elements. These clouds, known as giant molecular clouds, dot every galaxy. And it was in the early 1900s that British physicist Sir James Jeans discovered a process that would allow for these clouds to turn into stars. Jeans proposed that if the balance of a cloud was affected, then it could begin a process of runaway collapse. That balance could be disturbed by anything. However, usually, star formation is triggered in a cloud when it passes through the spiral arm of a galaxy. While spiral arms appear to dominate galaxies, they're really not that much denser than the gaps in between, containing roughly only 10% more material. The members of the galaxy, like the molecular clouds, orbit at different speeds, and so they pass in and out of the spiral arms. But when they pass through, a new round of star formation ignites, dominated in brightness by large stars, stars that die off before the cluster makes its way through the spiral arm, making the arms appear brighter and giving a galaxy its visible shape. Once a molecular cloud is set in motion, it can become destabilized and collapse, with its own gravitational pull triggering a feedback cycle. Most of the material coalesces towards the center, where friction heats it to high temperatures, becoming a protostar. The material that surrounds it spins and eventually forms a flat plane around the protostar, the beginnings of a protoplanetary disk. Much of the disk is made up of hydrogen and helium, but sprinkled throughout the swirling chaos is dust. And just like the dust that clings to the surface of your home, the dust in a protoplanetary disk sticks together. Meanwhile, as the process of planet building is underway, the protostar in the center begins to transform. Initially, it's heated from the outside in, as gas falls onto the core and slams into it. But towards the end of the protostar stage, just on the cusp of becoming a fully fledged star in its own right, it begins to heat itself from the inside out, releasing heat and energy in the form of radiation. And finally, after all the convulsions and chaos, the protostar ignites fusion in its core and settles into a hopefully long life. Within the inner regions of the disk near the young star, only the heavier elements, like iron, carbon and silicon, and their molecular combinations can survive, and so the inner regions of a solar system become the home of terrestrial, rocky worlds. But beyond the demarcation line, the glare of the young star is feeble enough over the great distances to allow ices of water, ammonia and nitrogen to remain solid. These ices mix with the dust and dirt, creating planetesimals that are far larger, and this increased gravitational pull sucks in massive envelopes of gas. The first planetesimal to form wins the gravitational prize, becoming the largest planet thanks to its ability to monopolize the gas of the disk. And so the next giants to form must fight amongst themselves over whatever is left. And these intense gravitational battles end up ejecting many planetesimals and even some planets out of the solar system altogether. In our own solar system, the giant planets formed much closer towards the Sun, where there was enough material to create their massive sizes. But as the disk cleared out, the mutual gravity of the planets pushed them outwards to their present positions. Indeed, there may even have been a fifth large planet